When looking at numbers, we encounter an endless expanse, but physical intuition fails us because not all infinite expanses share the same mathematical laws. This diagram shows the four standard number systems nested within one another: the natural numbers, the integers, the rationals, and the reals. Do these sets represent the exact same size of infinity, or are there distinct, larger degrees? If a set never ends, you cannot measure its size by counting to a final element. We need a rigorous functional workaround to compare them. This animated diagram demonstrates the solution, a bijection. A bijection is a perfect one-to-one mapping, where every single element in one set connects to exactly one element in another, leaving nothing unmatched. If we can create a perfect bijection between any complex set and the simplest infinite set, they have the exact same size. We call any set that passes this test countable. Our baseline metric is the set of natural numbers, commonly written as n. These are the basic counting numbers, starting at 0, 1, 2, and continuing upward forever. This is the first degree of infinity. It serves as our standard unit of measurement. We are going to test this standard by attempting to map it against sets that appear physically and geometrically larger. The rules are strict. If we can map a set perfectly to the natural numbers, it shares that baseline size. If that mapping fails, we have found a mathematically larger universe. Consider the set of integers, extending infinitely in both the positive and negative directions. Intuitively, it feels like it contains twice as many elements. If we try to map the integers by counting straight down the positive side, we run into a logical trap. We will count forever and never begin to assign values to the negative numbers. As this number line shows, a true bijection requires a different path. We start out at 0. We alternate. We assign 0 to 0, then jump to positive 1, back to negative 1, over to positive 2, and back to negative 2. This alternating formula guarantees that every single integer, no matter how deeply negative, is assigned a specific position in our sequence. The physical symmetry is an illusion. Mirroring the timeline into a negative dimension does not increase the size of the set. The set of integers is completely countable. Next, we test the rational numbers, fractions like 1/2 or 3/4. This is a dense set, meaning that between any two whole numbers, there are infinitely more fractions. You cannot count straight down a continuous line when there is infinite depth between any 2 points on that line. We can visualize the solution on a Cartesian plane, translating every fraction into a coordinate pair of integers on a grid. But we cannot simply count across the rows here either. The first row goes on forever, meaning we would never finish it. The valid mapping strategy spirals outward. We start at the origin and sweep through the nodes in an expanding diamond shape. By spiraling out from the center, we guarantee that the sweeping vector will eventually cross any coordinate pair, no matter how distant it is from the origin. Our geometric intuition is flawed. An infinitely deep, two-dimensional plane of rational numbers contains the exact same amount of elements as a simple one-dimensional counting line. In the 1870s, the mathematician Georg Cantor challenged the assumption that all infinite sets were equal. He tested the real numbers. To isolate the problem, he focused strictly on a subset, the infinite decimals located precisely between 0 and 1. We can simplify this subset even further for the proof by restricting it purely to infinite sequences of binary digits, zeros and ones. Cantor approached this using proof by contradiction. We will assume that this subset of binary decimals is countable, which means we can write down an exhaustively enumerated list. Here is our perfectly ordered master list. The left column indexes the rows sequentially, and the right column contains the corresponding infinite sequences of binary decimals. If this list truly contains every possible sequence, we should never be able to create a new sequence that does not already exist somewhere on this board. Cantor's extraction method steps diagonally down the matrix. We select the 0th bit of the 0th row, the first bit of the first row, and the second bit of the second row, extracting a completely new sequence. Now we apply a logical NOT operation. We flip every 0 to a 1 and every 1 to a 0, creating our red contradiction sequence. Does this newly constructed sequence exist anywhere on our allegedly complete master list? It cannot exist in row 0 because we flipped its 0th digit. It cannot exist in row 1 because we flipped its first digit. It clashes infinitely as it cascades down the board. The mechanical rule of this extraction ensures that the new sequence differs from the nth row at exactly the nth position. It is entirely unique from every item on the list. Because any attempt to list the sequences allows us to mathematically build a sequence missing from that exact list, the set can never be mapped. It is an uncountably larger infinity. The binary sequences we just failed to count represent a microscopic fraction of the real numbers. They are only a subset of the space between 0 and 1. Returning to our concentric circles, if we cannot map this tiny sliver, the entirety of the real numbers is vastly, uncountably larger than the natural numbers. The real numbers break the counting system because they include the irrational numbers, like pi and the square root of 2. You cannot combine two countable sets to make an uncountable one. Therefore, the irrationals themselves must be an uncountable infinity. There are infinitely more irrational numbers in the universe than there are rational fractions or whole numbers combined. We have identified a small, countable infinity and a massive, uncountable infinity. The next logical question is whether an intermediate infinity exists strictly between them. This became known as the continuum hypothesis. Following Cantor's discovery, it stood as one of the most famous open problems in late 19th century mathematics. In the 1960s, Paul Cohen discovered the answer. Using standard set theory, this question is mathematically independent. Independence means it is physically impossible to construct a mathematical proof or disproof for the existence of this intermediate infinity. The rigorous study of infinity reveals the absolute structural boundaries of human logic, exposing a mathematical reality where truths exist without any available path to prove them.